Hey physicists, today we want to talk about moment of inertia. So if you remember, we're in the angular section, which deals with rotating objects, objects that are moving in circles. And when we talk about linear motion, we have this idea of inertia that's measured by mass, that is how much an object does not want to change its state of motion. So we're going to find the same thing when we talk about rotational objects, that there's an amount of inertia that we call moment of inertia, of how much it wants to not stop rotating or to not start rotating at that change in rotation. So if I picture, just kind of starting with the foundation here, I have maybe a disc, maybe this is to date myself, a record player here, where you put two objects on the record player. So that this middle circle is where the object is rotating around. And then there's something on point A here, maybe a stone, and another stone on point B. So what we want to know is which one of these has the greatest translational velocity. Now, remember that translational would be the tangent velocity. It's the linear velocity. And when we look at it, so I would think through that this is going to be going, part A is going to be going in a circle that is 2 pi r circumference, and stone B is going to be going in a circle that is 2 pi r. But because the radius of B is greater, then won't its velocity be greater because it will be covering a greater distance in the same amount of time as A does, because the velocity is proportional to the radius. So we would say that B is greater in that case. Now, the second question then is, which one of these has the greatest rotational velocity? And think through this. So remember that rotational velocity is the radians per second, which is your theta that you cover in the amount of time. Well, don't both of these cover the same amount of theta in the same amount of time? They both cover 2 pi r radians, which means that in that case, they're both going to have the same rotational velocity. Now, file that in the back of your head. That's going to become important here in a second. So let's talk about kinetic energy. So I have this object. Maybe this is a planet. The kinetic energy is where it's rotating around some object here, or maybe it's the sun. This is the Earth and the sun, or something else like that. So kinetic energy, remember, is going to be 1/2 mv squared. If I take the conversion that I know for my rotational uh, energy, my rotational velocity, and say the velocity is equal to the radius times the rotational velocity, or omega, and I plug that in, I get 1/2 mr omega squared. Now, if I square those and lump those, doesn't this look kind of like this equation up here, where I have the 1/2, I have this in the center, which will be analogous to the mass, and I have my velocity here, my linear up here, my angular there. And that is what we're going to call our moment of inertia then. So it's going to be our moment of inertia. And a moment of inertia, the symbol for it is an I. The unit for it is kilogram meters squared. So you can see that straight out of what we got up there. And it is how much a rotating object resists its change in motion. Now, it's not just as simple as how much mass there is. You'll notice that because of that radius, the moment of inertia also changes depending on what it's rotating around, where that axis of rotation is. For in general, though, based off of this example, our point masses, the moment of inertia is the mass times the radius squared. And if you look back on the cover sheet, you'll notice that that's what that was. Now, let's take and say then that that equation for kinetic energy is 1/2 I omega squared. It's going to be our general equation for rotational kinetic energy. Now, think through, what if I have 2 point masses that are rotating around the same object? Maybe this is the Earth and Mars both rotating around the sun, or the Earth and a comet, or something like that. So if I take each of those and I want to get the total kinetic energy, and I have K1 plus K2, then I have 1/2 M1 V1 squared plus 1/2 M2 V2 squared. I'm going to do the same thing I did over here, where I'm going to substitute it in that R omega for my velocity. So R1 omega, R2 omega. And then I'm going to do the same thing I did over there. Now, if I look at that, what do we know about the omega values? Aren't these two omega values the same? So in essence, I can pull out the half and the omega, and I end up with this, where I have 1/2 of that, of all of that, the moment of inertia of each of those, times the omega squared. Hey, what happens when we add those up? Isn't that like saying it's a sum value? So our more general equation for a moment of inertia is going to be that it is the sum of the mass times the radius is squared, mass times radius squared. So, sample problem. Here I have two masses. They're both 3 kilograms. They're hanging on a massless rod, and they're rotating around this point where the yellow line is. That's our axis of rotation. And if the whole thing is 4 meters, I'm going to say each one of those distances is 2 meters. So I have 3 and 3, and I'm looking for the moment of inertia of that system. So remember that it is mr squared, or the sum of mr squared. So I can take and literally, since it's 2 point masses, add the two together, mr squared plus mr squared, and plug in my values, 3 and 2 and 3 and 2, and I'm going to get a total moment of inertia of 24 kilogram meters squared. Okay, now let's take and do in a second sample problem, what happens if we move the axis of rotation? So now let's have it rotating around this 3 kilogram, like through the center of that 3 kilograms, so that this other 3 kilogram is going around all the way around the outside of it. When I do the sum of my moments of inertias, then I'm going to end up with mr squared, mr squared. Well, the first three has a 0 because it's on the axis of rotation. And the other three is going to have a 4 squared because it is 4 away from the axis of rotation. And when I solve for that moment of inertia, I get 48 kilogram meters squared. Now, how about a third one? What if we move that axis of rotation even farther over so that this whole system is rotating around that axis of rotation there? So this is now 2 meters out. This is 4 meters. They're still 4 meters away. And I can again do the sum of the moments of inertias. And I have 3 times 2 squared plus 3 times 6 squared, because it's the total distance for the third one here, and that gives me a moment of inertia of 120 kilogram meters per second. So the question then is, what happens as the mass gets further from the axis of rotation? You should notice that as that radius is getting bigger, that moment of inertia is getting bigger also, the I value increases. So there's another thing that we want to talk about that you have to know for in relationship to this moment of inertia, and that's called the parallel axis theorem. So in the parallel axis theorem, the moment of inertia of that system is equal to the moment of inertia of the center of mass plus the shift in the axis. So if you think through from this first sample, the center of mass of this system, since it's 3 and 3, is going to be smack in the middle where this is rotating around. Well, in the second one, we've moved that axis now watch my finger there, from this point over to that point. So now I can take the center of mass moment of inertia, which is, I'm sorry, the moment of inertia around the center of mass, which would have been the 24, and I can add to it the total mass, which is 6, and times it by the distance that the axes are offset. So because this is offset by 2, then that's what I would put in for my d squared. So for example, I would take that, and then I would put in 24 for my center of mass, 6 is my total mass, and then 2 was the shift in that. And notice that I get the exact same answer that I had earlier, the 48 kilogram meters squared. Same thing for this one. You try. So I'm going to take that equation, the parallel axis center of mass is equal to the center of mass and moment of inertia plus m times d squared. So I'm going to take and put in the 24 again. The total mass is still 6, but now my center of mass, remember the center of mass of the system is here, so I'm only going to have a d that goes from there to there, and that's going to be 4. And when I plug it in, I get the 120 kilogram meters squared. You do have to know how to do this. The key to it, though, is you have to know what the moment of inertia of the center of mass is to begin with. Sometimes you're given that, and sometimes you're not. Okay, so key idea, the moment of inertia depends on where the masses are and where the axis is. I think you heard that earlier on the last slide, but it's just good to repeat it. Moment of inertia depends on where the masses are and where the axis is. Now, the question next is, what if these aren't point masses? What if they are a rod? So what we're going to do is we're going to take and say, hey, doesn't this sum symbol also translate into an integral, where it's the integral of the radius squared with the change in the mass? If I have a uniform density, then I know that that density is the total mass over the total length of the rod. If it's a non-uniform density, then I know I can sum up the masses over the radius. And then sometimes you're given some equation, like the line density is 3x plus 4, or some other value like that, and you would have to plug that in. So let's do a sample. Here's a uniform density rod. And since we're going to have it rotate around its center of mass here, which means that if I go to the left, it's going to be negative L over 2. If I go to the right, it would be positive L over 2. And that's going to be my lengths that I'm going to use because you notice that we're going to have to integrate this. So if my moment of inertia is the integral of the radius squared with respect to the mass, then I'm going to take and say, hey, this radius and mass change according to each other, kind of the same way we did earlier where we had line density and the center of mass. So I'm going to solve this dm up here and say dm is lambda times dr and plug it in over here. Then when I do that, because it's a uniform density rod, can't I pull the lambda out of the integral? And then I'm going to integrate from negative L over 2 to L over 2. So I get 1/3 r cubed from negative L over 2 to positive L over 2. Plug in those values so I can pull the third out and then substitute in my thirds. And notice because this is cubed, that'll keep my minus sign, and I'll add the two of those together, and I end up with this, where it is the moment of inertia, it's lambda times L cubed over 12. Now, I don't want to keep the lambda in there. I want to take and do what we had in the top here, where I say lambda is the total mass over the total length. And so when I substitute that in, then it helps me simplify it. And I get that for a rod that is rotating around the center of its rod, a uniform density rod, its moment of inertia is this 1/12 mr squared. And again, you should be able to see that on the cover sheet that we talked about that I gave you earlier that has the list of moments of inertias. Now, let's take that same rod, and instead of rotating it around the center of mass, let's rotate it around one of the edges. So now my length is going to start at 0 and go to L because my rotational axis is on the end of the rod. I'm going to integrate r squared dm. Again, I'll substitute in that dr lambda for the dm. And because my lambda is a constant, I can pull it out of the integral. I can integrate that and get lambda 1/3 r cubed. Notice it's the exact same thing as we had over here, except now my from and to, my definite integral is different. It's from 0 to L, which makes this quite a bit easier because I don't have all this goofy fractional stuff here. So lambda over 3 L cubed uh, from well, the zero's there, so from L minus 0. Then I'm going to get rid of my lambda and substitute this m over L, and that gives me 1/3 ml cubed. And that should look familiar to you also. It's a rod that is rotating around the end of its rod. So it'd be like my pen is rotating around that point versus if it's rotating around the center point. Let's do the same thing, only let's use the parallel axis theorem now. So in the parallel axis theorem, we already know the center of mass is this 1/12 ml squared. So we can plug that in for the ICM. And then my total mass is going to be m. And the length, the distance that my axes were offset, so in the original one, my center, my rotational axis is there. And in my new one, it's there, which means it's offset by an L over 2. And then when I simplify all of that down, I end up getting a 1/3 ml squared. Amazing! Oh, I messed something up here. So this guy shouldn't be cubed. This guy should be squared, right? Because one of my L's will cancel out with each of those. Ah, I caught it. Next one, let's talk about what if this is an area? So a uniform density disk. Second verse, same as the first, it just becomes a little bit more interesting. So because this isn't line density now, I'm going to have a total radius of big R, and then imagine I'm going to integrate out over these really small r's all the way out to the total radius. So my sigma, which is my area density, is going to be the change in mass over the change in area, which is going to be dm. Now think through, I'm integrating each of the circumferences out by this with respect to the r. So I'm going to have the 2 pi r integrating outward with respect to r. If I have my total disk, kind of the same way up here, we had our total length, total mass, then I can say that this is the total mass over the total area, which would be big M over pi r squared, which is the area of everything inside the disk. So when I take and do that, I can substitute in for my dm value this, if I move all of this over to the other side, so sigma 2 pi r dr. Now, my sigma 2 and pi can all get pulled out of the integral, right? So I can do sigma 2 pi and then r cubed dr, and I'm going to integrate that from 0, which is the center of the circle, all the way out to big R. So I'm going to end up with sigma 2 pi, and then when I integrate, I get 1/4 r to the fourth from 0 to r is going to give me 1/4 r, big R to the fourth. And then I can take this sigma guy, which is my total sigma, and plug it in for that, which goes in there, m pi r squared, and simplify. So when I simplify all that down, so I'm going to have a pi goes away, I'm going to have a 2 goes away, I'm going to have an r squared goes away, and I'm left with 1/2 mr squared, which is the moment of inertia of a disk. Isn't that so cool the way this all works out? So in summary then, the moment of inertia is how much an object resists a change in its rotational motion, right? Key idea there, it's rotational motion. So moment of inertia is how much resistance change in rotational motion. Rotational motion. The symbol for it is an I. The units are kilogram meters per second, or sorry, kilogram meters squared. I always want to say meters per second. Kilogram meters squared. The equation for it is the sum of all of the point moment of inertias, or the integral of the r squared dm value. You can use the parallel axis theorem if you know what the center of mass moment of inertia is. Remember that this d, the major idea is it's the offset from the center of mass to the new axis that it's rotating around. The I depends on the distribution of mass and the axis of rotation. That's your M and your R value. That's what you would have to know for those. And then if you're talking about densities, this line density is dm over dr, or the total mass over the total length. Same thing for area density. You have dm over dA, or the area 2 pi r dr, or the total mass over the total area. And then when we talk about volume, I left these just the general equations, dV and V, because those are really going to depend on what the object is that you're integrating that over. For instance, if I have a sphere, then I'm going to be integrating with a much different shape here than if I have maybe a cylinder that I'm integrating down the length of the cylinder. Both of those will have different values. So that in a nutshell is moment of inertia, and how you would find the moment of inertia of a rotating object.